Yeah, hi. This is Don Banfield. Thanks for giving me the anchor leg for this relay to bring us to the finish line. So I'm at NASA Ames. I'm fundamentally an atmospheres guy, but I've moved into instrument development of late. And I'm working with the FIG group that Amanda spoke about earlier. So here's our team. We've got the FIG people from NASA Ames, and a key industrial partner is Ian Neeson at VN Instruments. Who builds our transducers and some of the electronics. And we're also working with a group at Cornell led by Alex Hayes and mainly with his grad student Bianca Margara to do some field testing. So next slide, please. I'm going to tell you about basically a spin-off of a set of acoustics-based instruments that we've got that originally started with a Mars sonic anemometer, and that evolved into being a saltation sensor that we are in the process of maturing up right now with funding. And we think that this same kind of thing could be applicable to this plume-surface interaction that you guys are all talking about. And so we're hoping to adapt it to lunar applications as well. So let me tell you that thought process. Saltation, which we heard a little bit about yesterday, is the process where windblown grains move along the surface. It turns out it's really important for Mars, and yet it's still poorly understood. So we have this instrument to help understand it. And what we would argue is one of the most important things to measure to understand saltation is to, at the same time, get some quantitative measurements of the grain flux, the impact rate that is, and the size and speed and position of those grains. So we've built this sensor that can yield not only when it gets hit by something, but also tell you the speed and the size of the grain that's hitting it. So we would argue that that is also very similar to what you'd want to understand for understanding rocket ejecta plumes and their interaction with surfaces. The difference mainly between saltation and these rocket ejecta plumes is the speed of the grains. So wind-driven stuff gets to be of order 1 to 50 meters per second on Mars and Earth, but my understanding of the rocket ejecta plumes is the grains may be moving somewhere between a couple hundred meters per second up to a couple kilometers per second. So in many other ways, our instrument can just be ported over and taken to the moon, but we have to change our transducers, our sensor heads, so that they could survive and respond well to these high-speed particles. So next slide. I don't really want to spend a ton of time on this. This was a traceability matrix we put together to keep ourselves honest that we were aiming towards the right things that could actually satisfy the science that we're aiming at. On the left, in the upper box, is basically operational safety, which traces to the decadal survey and includes rocket blast ejecta. Below that, not so directly relevant to this conversation, but also important, is that we'd like to understand impact secondaries and how they modify the lunar surface. Both of those, we argue, can be furthered by understanding the grain flux, speed, and size as a function of time and place on the moon. And again, further, we would argue that to do that well, in addition to things like cameras, 3D cameras, nephelometers, maybe, as we heard earlier, millimeter wave radar units, you would want to have impact sensors as well. And ideally, as I argued before for saltation, those impact sensors should not only tell you the rate that they get impacted, but the size of the grains that are hitting them and the speed of the with which they impact at. And we established some requirements on the far right here. Hopefully those are appropriate, and most people in the crowd would agree with that. But please do let me know if we've missed the mark on something on that. We try not to overclaim. Notice that the mass resolution is not tremendous, but when you're talking about particles that range between 30 microns and maybe a millimeter, it's a pretty huge mass range. So that's actually pretty well resolved. Okay, next slide. How are we doing this? I said this was based on a family of acoustics instruments that we use. Originally a sonic anemometer to measure wind speeds on Mars. The business end of that instrument is what's called a capacitive transducer. And in the upper right, there's a couple pictures of them. So basically, this is a speaker microphone that is a capacitor. The front is charged one way and the back is charged a different way. And when either sound or a particle hits the front face of it, it oscillates, and that moves charge back and forth between the sides of the capacitor. And you can measure that with an amplifier sitting between that. So it creates an electrical signal. The advantage of this approach is that it's very sensitive because the membrane can be made very light. And it's broadband. You could compare that to piezo instruments, which are often used in the field to detect impacts. And those pretty much ring like a bell. So if you hit them, all they do is ring at one tone and then stop ringing after a certain amount of time. These, on the other hand, people use capacitive transducers like this as high-end hi-fi speakers. So they're broadband in general. They can produce a wide variety of time series of electrical signals or acoustic signals. And how that's valuable for us in this case is when you hit this with a grain, it makes a different sound depending upon whether it's a big grain moving slowly or a small grain moving quickly. So you can independently extract not only the impactor energy, but separately its momentum. And that's because we have this rich acoustic signal that comes from each impact. And it also rings down pretty quickly. It doesn't sit there and just oscillate for a long time. And that means that in about 1 millisecond, you're ready to record another impact. So this sensor head could record it up to about 1,000 impacts per second. And we would tune the area of the detector to match the expected flux so that we wouldn't become saturated easily. We can make these bigger or smaller quite easily. So the big change we're trying to make to adapt this to a lunar application is to harden it against much faster impacts. We made it as sensitive as we could to first make it a really good microphone for acoustics, but also to detect small, slow particles that are wind-driven. So the way we sensitized that was by using a carefully crafted backplate to it. In the upper right image, at the lower left of that is the backplate. And then the face of it is this aluminized mylar film that we made as thin as possible to make it sensitive for slow particles. But we can use a much thicker film to make it more robust against higher energy impacts. That probably isn't going to get us up to 2 km/s impactors. Those would still rip through any mylar membrane we would use. The option there is to basically flip the instrument around so that we present to the impactors a hard metal face, and on the back side of it is the aluminum that oscillates on the impact. So the aluminized mylar that oscillates on the impact. So the soft side is not exposed to the impactor, but the hard side is. That we haven't yet built. We have some designs for them, but that's what's in the process of development for us. So basically, I say we're going to turn them inside out. So next slide, please. Okay, so in the upper right just shows the electronics we already have. We can basically use the same electronics we have for our Mars sonic anemometer and for our Mars and Earth saltation sensor to monitor this instrument if we flew it to the moon. What we have to change is the transducers, like I said. So what we've got in plan is an iterative development plan where we'll take our existing prototypes and we shoot them with this BB gun that we've developed that can shoot well-known particle sizes in the sub-millimeter range up to about a couple 100 meters per second and down as low as a few meters per second. That's great for our saltating application, and it works for maybe the slowest speeds that we'd see at rocket plume ejecta. And so that helps us get going. It's very easy to use in the lab. But we eventually plan to take our prototypes after a few generations of evolution to the Ames vertical gun range that we heard about in a previous talk, and expose it to much faster impactors up to about 2 km/s, and iterate again on that to make sure we have some pretty well-evolved transducers that do a good job. Next slide. It's just a quad chart for the DALI proposal that is hopefully going to fund this work. I don't think I really want to say much about this other than we've proposed to DALI. We hope we're going to get funded, and we'd like to mature this up. We think it can be a pretty straightforward process because we have a fair amount of experience with these transducers. And like I said, the electronics is pretty much already pretty well developed. So anyhow, I'll leave it there. Thanks very much.